So, welcome to my lecture series on mathematical methods and its applications. So, we were in the last lecture we were discussing about convolution theorem, I mean convolution function, how, what do you mean by convolution of two functions. So, I told you that convolution of f and g is nothing but it is 0 to t f u g t minus u du. So, this is how we can define convolution of two functions. So, we have already defined some properties of convolution of two functions, that is it satisfy commutative property, it satisfy associative property and distributive property. Also we have seen that convolution of 0 and f is nothing but 0, but convolution of 1 with f may not be f, sorry, convolution of 1 with any function f may not be f, that we have already studied. Now we will come to the main topic, that is the convolution theorem for Laplace transforms. Now what this theorem states? It states that if Laplace transform of ft is say fp and Laplace transform of gt is say gp, then Laplace transform of convolution of f and g, which is nothing but Laplace transform of integral 0 to t ft g t minus u du is nothing but fp into gp. That is what convolution theorem states. Now it has, now what is the proof of this theorem? Let us see what is the proof of convolution theorem. So convolution theorem basically states that Laplace of f star g, which is a convolution of two functions f and g, is nothing but is equal to Laplace of. So this is the convolution definition of convolution, it is 0 to t, this is f u g t minus u du is equal to fp into gp. So this fp is nothing but Laplace transform of ft and this gp is nothing but Laplace transform of gt. So now let us see the proof of this theorem, convolution theorem. So what is Laplace of 0 to t f u g t minus u du? So this is nothing, this expression is nothing but convolution of f and g, that is why we call it convolution theorem. Okay. So how we define Laplace theorem? Laplace of some function f t. So Laplace is nothing but it is 0 to infinity e ki power minus p t, and instead of f t we have this entire expression. So this is nothing but integral 0 to t f u g t minus u du and whole multiplied by dt. This integral is over t. So this is what we define Laplace transform of this function say capital F t. Okay. Now this can be further written as 0 to infinity 0 to t e ki power minus p t f u g t minus u du dt. So this is how we can define this expression. Now basically we have to show that this expression is nothing but Laplace transform of f t into Laplace transform of g t. This we have to prove. Okay. So so in order to evaluate this expression or to simplify this expression, we will use change of order of integration. Now this is the limit for u. First we have a du. So this is these are the limit for u, and this is dt. These are the limit for t. Now let us draw the areas first. What is this area represent? This is u, this is t. Now u is varying from 0 to t. U equal to 0 is along this line, along t axis, and u equal to t is this line. This is something u equal to t. Now t is varying from 0 to infinity, that is t is varying from 0 to infinity means this entire expression, t is varying from 0 to infinity. Now first we have du here, that means we have to take a strip along u axis. So if we take a strip along u axis, say over here, either it is here or it is here, because both expressions are in positive side. It is 0 to t, that is in the positive side of u, it is 0 to infinity, that is on the positive side of t. That means it lies in the first quadrant area, whatever area this satisfy lying in the first quadrant. Now in the first quadrant, either this is this part or this is this part. Okay. Now to check whether this is this part or this part, first take a strip parallel to u axis. So take a strip parallel to u axis. So I am assuming that this is this part. If this is not satisfied, I directly go to this part. Okay. Now if I take a strip parallel to u axis over here, so what is u here? 0. What is u here? T. U is varying from 0 to t, and t is varying from 0 to infinity. So that means this is the entire region which is covered in this region, covered in this double integral. Now in order to change the order of integration, I have to make a strip parallel to t axis. So take a strip parallel to t axis now. So take a strip parallel to t axis. Now suppose this is a strip parallel to t axis. So this is further equal to, now double integral. Okay. This double integral. Now these are the limit for t, this is the limit for u. Now what is t here? T here is u. What is t? What is upper limit of t? It goes up to infinity, and u varying from 0 to infinity. U varying from 0 to infinity, entire range. Okay. So it will be e की power minus pt fu g t minus u. Now it is dt into du. So this is how we can change the order of integration. First we will see that here it is du. To mark that which region this double integral have, you take a strip parallel to u axis first. Okay. Now you take a strip parallel to u axis, you fix whether these limits are covered or not. If not, then take the other region. If yes, then mark this region, and in order to change the order of integration, take a strip parallel to t axis now. Okay. So this is equal to this. Now this expression is further equal to, now in this we make a substitution, take t minus u equal to some other variable z. So now let t minus u as some variable z. So what will be dt? It is dz. Okay. So this expression I am talking about this expression which is u equal to 0 to infinity, t from u to infinity, and it is e की power minus pt, then it is fu, then g t minus u, then it is dt du will be equal to, u remain as it is. Now t, when t is u, z is 0, and when t is infinity, z also tends to infinity, so it is infinity. It is e की power minus p, t is nothing but, t from here is u plus z into f of u remain as it is, because now we are not changing u, we are changing t. Okay. So g of t minus u is dz, I mean gz, and dt is dz, and it is du. Okay. And this expression is nothing but Laplace of convolution of f and g. Okay. So this is equal to this expression, and this is equal to this expression. Now it is further equal to, this expression is further equal to, so this is further equal to 0 to infinity, 0 to infinity again, it is, these are the limit for z, these are the limit for u, e की power minus pu fu, okay, and it is into e की power minus pz dz gz dz du. So, since now the variables are separated, u variable and z variables are separated and limits are constant. So, we can always write it as 0 to infinity e की power minus pu fu du into 0 to infinity e की power minus pz gz dz, and this is nothing but Laplace transform of ft. Okay. You say ft or you say fu, both are same because it is a change of only variable, okay. And this is nothing but Laplace transform of gt. You call gd or gt or you call gz, all are same, okay. So, this is nothing but fp into gp. So, we have shown that convolution of f and g, which is equal to this expression, is equal to Laplace of ft into Laplace of gt. Hence, we have proved this convolution theorem. Now, similarly, we can also state on this we can also state inverse Laplace transforms for this theorem. Now, if Laplace inverse of fp is ft and Laplace inverse of gp is gt, then Laplace inverse of fp into gp, which is the product of two p functions of two p's, I mean, is nothing but convolution of f and g, that is 0 to t ft gt minus u du. That is directly from the convolution theorem itself. Okay. So, first let us again rewrite the convolution theorem here, that is Laplace transform of 0 to t fu g t minus u du is nothing but fp into gp. And what is fp here? Fp is Laplace transform of ft and gp is Laplace transform of gt. This is by convolution theorem. Now, let us use convolution theorem to find out Laplace inverse of some functions. So, the first problem. So, this is nothing but p upon p square plus 4 whole square. So, this can be solved, this is equals to Laplace inverse of, you can easily find p square by 4 into 1 upon p square by 4. You can easily split this function into two sub functions fp and gp. You can call any one as fp, you can call the other function as gp. Suppose this is fp, suppose I am calling this as fp and suppose I am calling this as gp. So, what is Laplace inverse of fp? This is nothing but Laplace inverse of p upon p square plus 4, which is directly we can say it is cos 2t. So, suppose you are calling it ft, okay. Laplace inverse of fp, we call it ft. Now, second is Laplace inverse of gp, and gp is nothing but 1 upon p square plus 4. So, you multiply and divide by 2 and this is nothing but sin 2t. So, this is 1 by 2 sin 2t. So, say it is gt. Now, again to find out Laplace inverse of product of these two, we use if you use convolution theorem. So, this is nothing but the Laplace inverse of this product is nothing but 0 to t ft gt minus u du. So, Laplace inverse of this expression p upon p square plus 4 into 1 upon p square plus 4 is nothing but 0 to t. Now, what is ft? Ft is Laplace inverse of this function, this is nothing but cos 2t, cos 2u into, so it is cos 2u into 1 by 2 sin 2 t minus u du. Okay. Now, in order to simplify this expression, this is nothing but 1 by 4 integral 0 to t 2 times cos 2u into sin 2 t minus u du. So, this is 2 sin a cos b, 2 sin a cos b, so 1 by 4 integral 0 to t. So, it is sin a plus b. So, sin a plus b is 2t. So, you are calling it as a is b, and sin a plus b plus sin a minus b. Into du. Okay. So, this is nothing but 1 by 4. So, it is sin 2t will come out. So, integral of du is u from 0 to t, okay, and sin 2t minus 4u is nothing but integral is minus cos 2t minus 4u with respect to u. So, it is minus 4 will come in denominator, and it is 0 to t. So, if you simplify, we will get the final answer. The final answer will be nothing but 1 by 4 sin 2t into t, and minus minus plus 1 by 4 multiplication with, when you take u as t, it is cos 2t. When you take u as 0, it is minus cos 2t. So, this term will cancel out. So, this will be the final answer of this problem. Now, similarly, the last problem we can solve using convolution theorem. So, what is it is Laplace inverse of 1 upon p minus 2 into p plus 2 whole square. So, this is Laplace inverse of fp into gp. So, Laplace inverse of fp will be nothing but Laplace inverse of 1 upon p minus 2, which is nothing but e ki power 2t, and Laplace inverse of 1 upon p plus 2 whole square will be nothing but e ki power minus 2t. You will apply shifting property e ki power minus 2t into Laplace inverse of 1 by p square, which is nothing but t. So, it is t e ki power minus 2t. So, this is, you can say anyone as ft and anyone as gt, okay, because convolution of two functions satisfy commutative property. Okay. So, Laplace inverse of fp into gp is same as Laplace inverse of gp into fp. Okay. So, this is nothing but 0 to t fu g t minus u, g t minus u du. So, this is by convolution theorem. You can use this also, no problem. Okay. The only thing is I have simplified this, because otherwise t minus u comes in both the expressions. Okay. So, this will be nothing but e ki power 2t will come out. So, it is 0 to t u into e ki power minus 4u du, and now you will apply integration by parts. So, it is nothing but e ki power 2t. So, when you integrate by part, it is u e ki power minus 4u upon minus 4 minus this derivative integral of second is e ki power minus 4u upon 16, and the whole expression from 0 to t. So, when you integrate from 0 to t, so the final answer of this expression will be nothing but e ki power 2t will come out. When you substitute u as t, it is minus e ki power minus 4t, and when it is 0, so it is minus minus plus. Okay. When u is 0, it is 0. Now, when it is t, it is minus of e ki power minus 4t upon 16, and when it is 0, so minus minus plus it is 1 by 16. So, I simplify this, this will be the final answer of this problem. This is how we can find out Laplace inverse of this expression. Now, let us see some more problems based on convolution theorem, which otherwise is very difficult to actually find out. Okay. So, let us see Laplace inverse of these functions also using convolution theorem. So, what is the first problem? Let us see Laplace inverse of p upon p square plus 9 whole cube. Now, how to find Laplace inverse of this expression? Okay. So, so it can be break into two functions. Suppose one function is p upon p square upon 9, and suppose other function is 1 upon p square plus 9 whole square. Now, if you split into this form, if you split into this form, so finding Laplace inverse of this is difficult. We take p over here and 1 over here. Okay. So, that because otherwise 1 upon p square plus 9 whole square Laplace inverse is difficult. Okay. So, okay. Now, now let us suppose we already know that Laplace inverse of this is suppose this is Fp and suppose this is Gp. So, Laplace inverse of Fp we already know it is nothing but 1 by 3 sin 3t, and that we can easily find out. Okay. Now, to find Laplace inverse of this expression we have two methods. Either we again apply convolution theorem in this expression separately, find Laplace inverse of Gp, which again can be written as function of product of two functions. Are you getting my point? I want to say that let us write this as p upon p square by 9 into 1 upon p square plus 9. Okay. And suppose this is some function, this is some function, and again apply convolution theorem to find out Laplace inverse of this expression. Or the other way out is, whatever methods we have studied, whatever properties we have studied for Laplace transforms, find out Laplace inverse of this function using those properties and directly substitute it over here. So, choice is ours. Okay. So, let us find Laplace inverse of this function using the earlier properties which we have already discussed. So, suppose though this is suppose some kp, function of kp, let us suppose, because fp we have already used, so we are using some other function of p, is 1 upon p square plus 9. Okay. So, k dash p is nothing but minus 2p upon p square plus 9 whole square. So, now Laplace inverse of k dash p is nothing but minus 2 times Laplace inverse of p upon p square plus 9 whole square. We want to find out Laplace inverse of this expression. So, what is f dash okay. Laplace of t f t is nothing but minus 1 ki power 1 f dash p. So, actually we have to use this property. Okay. Actually we have to use this property. So, Laplace inverse of f dash p is nothing but minus t into f t, and f t is Laplace inverse of k p, is minus 2 Laplace inverse of p upon p square plus 9 whole square. So, minus minus cancels out. Okay. So, this is nothing but t into. Now, what is Laplace inverse of this expression? This is 1 by 3 sin 3t. So, it is 2 Laplace inverse of this expression. So, Laplace inverse of this expression is nothing but t by 6 sin 3t. So, this is Laplace inverse of this expression. So, basically Laplace inverse of Gp is nothing but t by 6 sin 3t. So, this you can also find out using convolution theorem. I told you this we can easily find out using convolution theorem also. Okay. Now to find Laplace inverse of the product of these two, that is Fp into Gp, Laplace inverse of Gp into Fp or Fp into Gp, both are same. So, Fp into Gp is nothing but 0 to t. Now, the first function is this. This is Fu, u by 6 sin 3u into gt minus u du, into gt minus u, that is 1 by 3 sin 3 t minus u into du. So, this is nothing but u by 1 by 18. You again multiply and divide by 2 to integrate this. So, it is 1 by 36, I can write here 1 by 36, it is 0 to t u. Now, when you multiply and divide by 2, it is 2 sin a sin b, which is nothing but cos a minus b minus cos a plus b. So, it is cos a minus b. So, cos a minus b is nothing but 6u minus 3t and minus cos a plus b. So, a plus b is nothing but 3t into d. So, now this you can easily integrate using method of using by parts, and you can easily find out Laplace inverse of the first problem. Okay. Now, the second problem, let us say the second problem. Okay. Laplace inverse of the second problem. Laplace inverse of p square upon p square plus 1 whole square into p square plus 4. Again, you have to split into 2 in such a way that Laplace inverse of both the functions you can easily find out. Then only we can apply convolution theorem. Okay. So, it is p square upon p square plus 1 whole square into p square plus 4. So, it is Laplace inverse of p upon p square plus. So, either you can split into 3 and apply convolution theorem 2 times. It is again it is our choice, or you split into 2 and apply Laplace theorem only once, I mean convolution theorem only once. So, this you can do like this into this and this into this. Now, Laplace inverse of this we already know, this is nothing but cos 2t, which is ft or gt, anything. Okay. Now, Laplace inverse of this. Okay. Laplace inverse of this again you can find out using the previous problems, as in the previous problems we did finding the f dash. Okay. We can easily find out, because you can take fp as 1 upon p square plus 1 and then find the derivative as f dash p is equals to minus 2p upon p square plus 1 whole square. Then taking the Laplace inverse both the side, it is minus t ft is equals to minus 2 times Laplace inverse of p upon p square plus 1 whole square, and minus t ft is nothing but Laplace inverse of this, which is sin t, it is equal to minus 2 Laplace inverse of p upon p square plus 1 whole square. So, Laplace inverse of this is nothing but t sin t by 2. So, this is a, this is ft. So, to find out Laplace inverse of these two is nothing but 0 to t ft and gt minus fu The first always involved u, fu, gt minus u, that is cos of 2 t minus u into du. So, one can easily integrate it again by integration by parts and find out the Laplace inverse of this expression. So, thank you very much.